Hello, this is Sumati, lecturer, Department of Electronics and Communication, SJ Government Polytechnic. So today, in the last session, we went through different input and output instructions that can be used with the PLCs, and then we also went through how to program the contact and coils. We have seen number of examples in the last session. Now, today in this session, we'll be covering the logic gates, what a logic gate is, their symbols, what truth table is, what's a logic equations. So, all these things will be covered in this current session. I'm taking a session about logic gates because this is a prerequisite whenever you want to do the PLC programming. So you should know about the logic gates. So this is very important if you want to understand the PLC programming. So let's go through this logic gates very quickly. There are seven logic gates, and these logic gates are the building blocks of any digital circuit. So, our digital circuit can be constructed using these logic gates. These are the building blocks of a digital circuit. The working of a logic gate is given in the form of a truth table. Hence, the truth table completely describes how the gate will work. So, the function of a true gate is given in the form of a table called as the truth table. The input and output, the relationship between input and output of a logic gate is described in terms of logic equations, or it's also called as the Boolean equations. So your Boolean equations will tell you the logical relationship between the inputs and the output of a logic gate. These gates are now available in the form of a integrated circuits, ICs. So all the gates all the gates have except the NOT gate have two or more than two inputs, and all the gates have only one output. In case of a NOT gate, we have only one input and one output, whereas the other gates can have two or more than two inputs. Now we'll look at the types of logic gates. There are two types of gates. The first one is the basic gate. The basic gates, they perform the fundamental logic operations, and all logic functions or all logic circuits can be obtained by using these basic gates. Now, what are the basic gates? These AND or NOT gate. So these are the fundamental logic operations. So using these fundamental operations, now we can derive the other gates. So those second type of gates are called as derived gates. So here you have NAND gate, NOR, XOR, and XNOR. So all these four gates are obtained with the combination of AND, OR, and NOT gates. So they are called as derived gates. And here, AND, OR, NOT, these are the basic gates, whereas NAND and NOR gates are called as universal gates. They are called universal because any logic function, whether it is simple or complex, can be implemented by using only NAND gates or implemented by using only NOR gates. Hence, NAND and NOR gates are the building blocks of any digital circuit. So they are called as universal gates. Now, coming to the gates in detail, this I've shown is the symbol of a AND gate. Here, below the AND gate, I have shown a Boolean equation here. The Boolean expression is read as, it has to be read as y equal to a and b. So, the a and b are the two inputs, y is the output. So, in order to obtain the output y, this gate will do AND operation between the two inputs A and B. So the expression has to be read as y equal to A and B. And this AND gate resembles, when we correlate this to a analog circuit, the AND gate will correspond to two switches in series. So here you can have a look at the truth table of an AND gate. The output of an AND gate is 0 when both the inputs are 0. The output is 0 when any one of the inputs is 0. And the last case is the output of an AND gate is 1 only when both the inputs A and B are 1. The next gate we should study is the OR gate. Here I have shown the symbol of an OR gate, and below it is a logical or Boolean equation, y equal to a plus b I have written. So this expression has to be read as y equal to a or b. So in order to obtain the output y, I need to do the logical operation OR between the two inputs A and B. Here, let us go to the truth table. The output is 0 when both the inputs are 0. The output is 1 only when both the inputs are 1. The output is 1 when any one of the input is 1. So this OR gate resembles the two switches connected in parallel. So when one of the switch is enabled or activated, the circuit will be completed and the bulb glows. When both are activated, both the switches are activated, then also the circuit will be completed. When both the inputs or both the switches are not activated, in that case the circuit will be open, and hence the bulb will not glow. So your OR gate resembles or corresponds to two switches that are connected in parallel. Now let's look at the NOT gate. Here I have written the equation is y equal to a bar. So the line above the variable corresponds to complement or inversion. So the output of a NOT gate is the complement of its input. And this is evident in the truth table. Whenever the input is 0, the output of NOT is 1, and it is vice versa. Now let's look at the NAND gate. So the NAND gate Boolean expression is written as y equals a and b. Above that we have put a bar. So this indicate the bar indicates that it is a it is complemented. That is a dot b is first obtained, then it is complemented. Or in other words, we can say NAND gate consists of two gates. The first gate is the AND, which produces the product A dot B. That is, the first AND gate performs A and B operation. The second gate is a NOT gate, and this performs the complementary operation. That's why in the Boolean equation, I have written that NAND gate as A and B. Oh, above that variable, we have written a bar. So your NAND gate is a combination of AND gate and NOT gate. Now let's look at the truth table of a NAND gate. Here you can see when both the inputs are 0, the output of NAND is 1. And also when any of the input is 1, the output is 1. Similarly, when both the inputs are 1, the output is 0. So this output column what you are seeing on the screen is exactly the complement of the AND gate output. So NAND gate. Here you can see here I have written a NAND symbol, AND gate symbol, and then the output is inverted. So that inversion in the output is indicated in the logic diagram as a bubble. So I have put a bubble here. Bubble means first we obtain the AND operation of two input variables. After that, that result is inverted using NOT. So, in the symbol, that output at the output y, the output is it is bubbled. We say it is output is bubbled. Bubbled means whatever the output we get from the AND gate will be inverted. Now let's look at the next gate, which is our NOR gate. So here you can see the Boolean expression. It has to be read as y equal to a or b, a or b, and it is uh, complemented. So at the output you can see the variable y. Here you can see the output is being bubbled. You can see a small circle at the output of a OR gate. So the NOR gate is a combination of OR gate and a NOT gate. Now here you can see when both the inputs are 0, the output is 1. When any of the inputs is 1, the output is 0. And when both the inputs are 1, the output is 0. So this output column, what you see in the truth table is exactly the complement of the OR gate output. Now let's look at another gate, the XOR gate. Here the XOR gate, it is the Boolean expression is to be read as y equal to a XOR b. The XOR operation is indicated as encircled plus. So we have a plus here, and on the plus mark we have got a circle. So it is encircled plus indicates it's an XOR operation between two inputs. Here, looking at the truth table, you can see here when both the inputs are 0, the output is 0. Here in the last combination, when both the inputs are 1, the output is 0. Otherwise, the output will be 1. In other words, we can say the output of XOR gate is 1 only when both the inputs have different values. So this is evident from the truth table. You just have a look at the second combination and the third combination here in the truth table. Here A is 0, B is 1. So both the inputs are different. The A and B values are different. In that case, the output of XOR is 1. Again, in the you look at the third combination where A is 1, B is 0, and the output is 1. Here also the inputs have different value. So whenever the inputs have different value, the output of XOR gate will be 1. Now let's go to the last gate, the XNOR gate. And here the Boolean expression, you have a look at the Boolean expression. It is written as y equal to A XOR B, and above that I have put a bar, or I have complemented the output of XOR gate. So this XOR gate is a combination of XOR and NOT gate. That is, the output of XOR is complemented using NOT gate, and this entire combination of XOR and NOT is called as XNOR gate. Now let's look at the truth table. Here, the first combination, when both the inputs are 0, A is 0, B is 0, the output is 1. And the second and third combination, you have a look at it, the both the inputs have different values. In that case, the output of XNOR is 0. In the last combination, that's the fourth combination, A and B have the same value 1. In that case, the output of XNOR is 1. In other words, I can say whenever whenever the inputs have same value, that is A and B have same value, in that case the output of XNOR gate is 1. So, so this is uh, about the logic gates we have studied in this present session. So let's recap it. So we went through this various logic gates, the symbols, truth table, and the equations. Then what about the input and outputs of a logic gate, how they are output and inputs, how they are related, and the working of a logic gate is given in terms of the truth table. So all these things, then we went through the types of gate, the basic gates and derived gates. Again, in basic gates, we went through in detail about the working of and, or, not. In derived gates, we went through NAND, NOR, XOR, and XNOR. And also, told you about why NAND and NOR are called as the universal gates, because any logic circuit, whether it's simple or complex, can be built using only NAND and only NOR gates. So they are called universal gates. We also went through the symbol of an AND gate, and what's the operation the AND gate does is it's an AND between AND operation, logical AND between the two inputs. The OR gate also does the logical ORing operation between the two inputs. And you can see here the AND gate output is 1 only when both the inputs are 1. For an OR gate, the output is 0 only when both the inputs are 0. And NOT gate is the output is exactly the complement of the input. Coming to the NAND gate, NAND gate is combination of and NOT gates. So the output of an AND gate is exactly the complement of the AND gate output. The NOR gate is it's the combination of OR and NOT gate. The output of NOR gate is exactly the complement of the OR gate. And we also went through the XOR gate, wherein the output is 1 only when the inputs have a different value. The last gate is about the XNOR gate, where the XNOR gate is the combination of XOR and NOT gate. The truth table tells that the output of XNOR is high only when both the inputs have got the same value. So after going through this session, now let's go for the multiple choice questions. Here I've got simple questions that you can try and answer. So the question number one is here I've shown a symbol of a logic gate, and this symbol represents which gate is the question. So here you have the choices AND gate, OR gate, NOR, and OR gate. Now you can try this. You can try to solve this. So the above symbol represents AND gate. So it's a symbol of an AND gate, and this gate does the AND operation between the input variables. Now the second question here you can see the symbol of a gate, and this gate represents an AND, an OR, and NOT gate. So try this question. Try to answer this question. This symbol represents NAND gate. NAND is it's a combination of AND and NOT gate. So the logic expression for the NAND gate is that y equal to a and b, and whole thing is complemented. So put a bar over a dot b. Now let's move on to the third question. Here I've shown a symbol here, and the symbol represents which gate? The choice are OR, NOR, XOR, AND. So the symbol represents XOR gate. Answer is choice C. It represents XOR gate. And the equation law Boolean expression for XOR gate is y equal to A XOR B. And XOR operation is represented by encircled plus mark. Alternately, this XOR operation can also be written as y equal to A bar B and A bar B plus A B bar. So plus indicates it's an OR operation. Dot is AND operation. Plus indicates OR operation. Let's move on to the next question, which is about the basic gates. Here, the basic gates are A and B or C not, D NAND. The choices I've given is it's A B C, B C D, A C D, A B D. Try this out. The basic gates are AND, OR, NOT. So the correct answer for this fourth question is it's the A, B, C. That is choice 1. Choice 1, which is A, B, C. That is A AND gate, NAND gate, OR gate are called as the basic gates. Whereas NAND, NOR are called as universal gates. Let's move on to the next question. The only gate that has single input is choices are and, not, or, nor. The answer is not gate. So all the gates except not have two or more than two inputs, whereas the NOT gate has only one input. So the answer is NOT gate. The only gate that has single input is a NOT gate. Now let's go through the last question. Which gate has its output on when inputs are different? That is, when the inputs A and B have got different values, the output is 1. For which gate this applies? The choices are NOR, XOR, NOT, XNOR. The answer for this is XOR gate. So for an XOR gate, whenever the inputs have different value, the output will be 1. And for rest of the cases, the output will be 0. So the correct answer for the sixth question is choice B, XOR gate. So I think we went through the basic knowledge about all these logic gates. So in the next session, we'll be studying about how to convert these logic gates into a ladder diagram. So, which is the ladder diagram is the fundamental concept used in PLC programming. So, in the next session, we'll see how these logic gates are converted into a ladder diagram. So, thank you.